In 287 BC, the great mathematical mind Archimedes was born. His best work is what we use today in math to help us find the area of a circle. But how did Archimedes find the value of pi? Let's look at how he solved it and some of our own tricks to find the closest approximation we can.
To approximate pi, we will draw a circle with diameter of 1. We do this because the circumference equals pi. We will place a simple shape in it, like a square, and find its perimeter as an approximation. We don't know anything about the lengths of the square besides some square things, like all the lengths are equal to each other, the diagonals are equal to each other, and they intersect perpendicularly. So let's use Pythagoras' theorem to find the side length that is unknown. So s squared is equal to a half squared plus a half squared. And we will work that out to be s equals 1 on root 2. But the thing about this square, it's not just the side length is the perimeter. The perimeter is the side times all of the numbers of sides. So that's 4 in this case. So we will multiply the side by 4, and we get 4 over root 2, or around 2.8, which isn't close to pi at all. I wonder if we can generalize pi just by this example. So to get a better answer, we can make a polygon with n-sided, but how would we find all the angles? Let's go back and look closer at the square attempt. Last time we just knew that the diagonals of a square intersected perpendicularly, but let's find another way of finding that. We know that circles have 360 degrees, so no matter how we divide it up, we're still going to get 360 degrees in total. And we see that the square had 4 sides. Then that must mean we divide the 360 degrees by 4 and get 90 degrees, which is what we had. So in our case, it must be 360 degrees over n sides, or just 360 on n. Now we have 2 sides and a known angle. So let's see if we can find the other side. So we'll make a generalized triangle with sides AA, BB, and CC.
What we want to do is draw an altitude so that we can use Pythagoras' theorem, and we'll label the altitude h, and the two sides we add from the altitude, x and c minus x. And the point where the altitude meets c is d. This way we can talk about the smaller triangles.
So now we have a labeled triangle, but right now that won't help us with what we're trying to find. So let's add some stuff to it, but ultimately we want to take it all away and make it as generalized as possible.
So in triangle DCB, we have a squared equals h squared plus the quantity of c minus x squared. This expanded is a squared equals h squared plus c squared minus 2cx plus x squared. And for triangle DCA, we have b squared equals x squared plus h squared. But like I said earlier, we want to cancel out what we put in. So we will solve for h in the second triangle and substitute it into the first triangle, getting rid of h. So now we have h squared equals b squared minus x squared, and we'll substitute that into the first equation, having a squared equals b squared minus x squared plus c squared minus 2cx plus x squared. Simplified and canceling out the x squareds, we have a squared equals b squared plus c squared minus 2cx. But we still have one pesky x. So let's see how we can relate x to the original angles that we had. So we look back at triangle DCA, and we see that it is a right triangle. So we can use trigonomic functions on it. And we can see that the cosine of A is equal to x over b. And solving for x so we can substitute it into the other equation to eliminate it, we get x is equal to b times the cosine of A. And plugging that into the equation and putting it in alphabetically to look better, we now have a squared equals b squared plus c squared minus 2bc cosine of A. So now that we have the equation to plug in our numbers, we can now generalize pi. So we take the triangles from both of the examples, and we try to find the unknown side. Once we do this, we can generalize pi. So we find the unknown side as a squared equals a half squared plus a half squared minus 2 times a half cosine of 360 on n. Simplify, factor out the 1/2, take the square root because the equation is for the side squared, and we end up with 1 over root 2 times the square root of 1 minus the cosine of 360 on n. So we can look back on our first equation to see that the perimeter was the side times the number of sides. So now we'll multiply by n, and now we get n over root 2 times the square root of the quantity of 1 minus the cosine of 360 on n. Now we will plug in a larger number and a smaller number to see which one is a closer approximation of pi. We will plug in the numbers 10 and 1 for n and see which one is closer for pi. We'll work them out, and 10 will be equal to 3.09 and 1 will be equal to 0. So now knowing this, we know that as the number increases, we get a better approximation of pi. So as the number grows infinitely larger or approaches infinity,
we get the best approximation of pi.